Yeah, thank you for letting us go first. That's really helpful. All right, so I'm Ryan. I'm representing Group B for Project Update 2, and our project is now called 3-deader to 4-deader object detection on LiDAR using FNET token mixing. So as a recap for the motivation and our objectives for this project, we're working with point clouds. Point clouds are generated typically by a system called LiDAR, and it's very often used in places such as autonomous driving, especially in low light conditions. They want to detect cars, people, and different objects like that from these different point clouds that are generated from LiDAR, and we want to do it accurately and quickly. And so our goal is to contribute to object detection on point cloud video using a transformer architecture. The point of the transformer architecture is we want simplicity. The transformer makes less assumptions about the problem at hand, and so it can use less hand-designed parts of the model. So it's a simpler architecture. And then we also want to make the model, we want to ensure it's still fast, just as fast as it was, at least without being in video. And we want to do this with a marginal trade-off in accuracy. So the baseline for our method is 3-deader, and this is what we forked as a base. Like I said before, this architecture is able to make less assumptions about the point cloud and use less of these pre-processing or like voxelization methods that other methods use. And the reason that this model is really cool for us is because of the way that it deals with object queries and in the decoder. So the decoder, well, as a good rule of thumb here, what we're trying to do is if we can make new predictions close to previous successful predictions, then we hypothesize we're going to end up with a better result. So this is where the object queries come into play. The object queries and the decoder are actually just positions that are picked out of the initial point cloud. So we can actually then update and tell it where to look in next frames based on previous predictions. And the goal is to improve evaluation performance through that process. And the interesting thing here is the model can then still be trained in 3D and can be evaluated on 3D benchmarks. That way, any changes that we're making to improve, for instance, speed, we can make sure that they're not really hurting the model on any of the original things that they were tested on. And then we can move it to maybe a more difficult benchmark and still be able to evaluate the changes we're making. This was inspired by Trackformer, which does a very similar thing to Deader, but on a 2D frame. This is 3-deader. Trackformer is from 2-deader. And so here's a diagram just to visualize that. We get these object queries and they go into the decoder, and then we interpret some boxes from the output. Then we can take the center of these boxes and we can replace some of the initial object queries with these same boxes. And hopefully, even though the representation of like a person is going to change a little bit across frames, especially if a vehicle is turning, they're still going to be located in about the same position, and we still want to be able to pick them up there. FNET is what we're trying to use to keep the model performant. FNET is a transformer-based architecture that does not use attention. It substitutes it with a Fourier transformation as a sublayer. And so to simplify that, it runs 2 Fourier transforms, one along the hidden dimension and then along the sequence dimension. And then it only keeps the real values because there's some complex numbers introduced from that. Here's what that looks like here. And what's the point of this? Well, we can get a performance gain for a negligible accuracy hit. That's what the original FNET paper was all about. And so we're trying 2 main architectures here. We obviously have the baseline, just 3-deader. We have our encoder and decoder structure. And then we have our FNET version of this, which is where we replace the transformer encoders with FNET encoders. And these come straight from the original paper, the FNET paper. So they're slightly different in terms of where exactly things are normalized and added together. But ultimately, the biggest change is just that the multi-head attention is replaced with this Fourier token mixing. The primary data set we're using and we have support for right now is Kitty 3D object detection. And this is the data set we've run our initial experiments on. And so I'll break down parts of this chart that are important here. These are preliminary results. So the model is broken down by 2 different thresholds. There's 0.25 and 0.5. This is intersection over union. So the stricter that we are in this metric, the lower number of detections we're going to have, just because it's a harder metric to meet. The query capacity is one of the hyperparameters we're fiddling with on the model. The higher number of query capacity that we give it, the more locations it has, the decoder has to look for objects. One thing we noticed initially, and the reason that in the query capacity, the initial model, we have 256 query capacity versus 512 is because when we initially had them all at 512, the model with both the encoder and decoder ran out of memory. And so we weren't able to complete that experiment, which does show that as long as we can keep accuracy in this Fourier model, and also another baseline model that we tried, which is just removing the encoder entirely, then this might be a benefit as well. We might be able to bump up the hyperparameters and get maybe even more accuracy. The runtimes are a bit difficult to compare because query capacity has an impact on runtime, but with double the query capacity, it did only take 50% longer. And this was 200 epochs. We will train it for longer according to the original 3-deader paper next week. And then Kitty breaks things down by class. So I'm going to emphasize car because this is one of the most important and also the one that it did the best on. And so we can see after 200 epochs, the 3-deader with the Fourier that we added into it was able to achieve a AP score of 41 and a recall of 52. Meanwhile, the transformer, which was trained for the same number of epochs, but we had to give it a lower query capacity, was not able to achieve as well. Although hopefully we do want to get a more apples to apples comparison next week. And also, just as I mentioned, we want to make sure that introducing FNET doesn't mess with the original accuracy, and we do want some gauge for how accurate we want it to be even on Kitty. So these are the original numbers. You can see the 25, it obviously does better because it's a lower threshold, but we still have some work to do in making up on the stricter threshold. So final steps, in our initial proposal and update, we wanted to use 2 different data sets. We're still going to be trying to continue that by the end of this week. So we want to finish integrating new scenes in. Then we also want to finish doing the actual video aspect of Kitty, because it's been difficult because Kitty is a massive data set and we have to do some shortcuts to get it to fit on our Newton accounts. Next week, we're going to run the actual experiments, training these 3 different models for much longer. The original paper did 1,080 epochs. We'll see what we can get. And then we want to finish we also, if we have time, we would like to do a little bit of tracking because the way that we're going from 3 to 40 blends very nicely into tracking because that's what we're effectively trying to do. And so if we have time, we'll try and introduce a tracking dimension on the side. And these are our references. That was the update.
So we are doing Tiny Actions Challenge. This is our project update 2, and we have Mehdi, me, Momal, Sanjay, Kasun, and Dane in our group. So I'm just quickly going to go over the introduction of the problem, the solution that we have proposed, the results that we have got from some preliminary experiments that we have tried, the limitations that we think are in our current proposed solution, and how we plan to fix it. So the problem statement is we are trying to perform action recognition or video classification on the Tiny Virat dataset, which is part of Tiny Virat challenge of CVPR 2022's activity network shop. And the task is that we are trying to perform multi-label video classification on Tiny Virat V2 video samples, which are low resolution video samples like one can be seen here. So the proposed solution that we have had so far, it's an adversarial super resolution feature learning network. Basically, we are taking a pre-trained video sync network, which acts as a teacher, and we have Vivid, which is our student network, a student video classification network. And basically, we are trying to compute the feature vectors for low resolution Tiny Virat video samples and high resolution Kinetics 400 video samples of same label. And after getting these low resolution and high resolution feature vectors, we are using a discriminator which tries to tell the low resolution and high resolution embeddings apart. And we let the gradients flow back to improve the student encoder. And the high-level idea for this network architecture is that we are trying to train a student encoder, a network, which takes low-resolution videos, but kind of maps it to a feature space which resembles high-resolution embedding, kind of what is generated by a pre-trained video swin for high-resolution samples. So yeah, the student network that we are using is a factorized encoder, second model of the Vivid paper. And the teacher network is a pre-trained Swin Tiny, which is pre-trained on Kinetics 400 and was initialized with ImageNet 22K. So the results that we've had so far is that we first off started with a pure baseline, which is a Vivid video classification network. We just trained it from scratch on the Tiny Virat dataset, and we got not fairly a good F1 score. It was like just 8%. Then our adversarial super resolution network with KL divergence loss is giving us almost 5% improvement over the pure tiny vivid baseline. So we're getting like 12% F1 score. Slightly changing the training setup from KL divergence loss to Wasserstein loss and gradient penalty is giving us 0.0096% improvement in F1 score. So this is the best F1 score that we have so far. And if we compare it with the top score of the leaderboard, we still have a long way to go, because the leaderboard top scorer is getting approximately 46% F1 score. And the R2 plus 1D video classification network based baseline, which is proposed by the competition organizers, which is by UCF, it's almost 32%. So our current result is below the baseline and the top scorer. So we kind of analyzed what are the limitations with our current solution. So the first thing that we think is messed up is the varying data distribution of teacher and student network. So we see that the student network is taking samples from Tiny Virat and the teacher network is taking samples from Kinetics. Although the samples are of the same label, but still the data distribution of Tiny Virat and Kinetics data set is quite different. And that might be a reason for student network to not to be able to perform well on the downstream video classification task of Tiny Virat, because we think probably the student network is trying to transform the Tiny Virat samples to be more like the Kinetics 400 sample in this setting. So that we think is one drawback. Second, we also think that there are architectural differences between teacher and student network. So the student network that we have here, it's a Vivid, and the teacher network that we have chosen is a video swin. So the way attention is computed and the relative position biases, there are a lot of differences between these two architectures. And we think due to limited learning capacity of Vivid as compared to video swin, because video swin has outperformed Vivid on a bunch of other high resolution data sets. So we think because students don't have enough learning capacity, that might be a reason for which the student is not doing too well. Third limitation, we think in our cases, we haven't tried any data augmentation techniques yet. And in original Tiny Virat V2 dataset, we have almost 17,000 training and 3,000 validation samples, which we think is quite a smaller size for data hungry transformer-based network architectures like this. So we are planning to go in the dimension of exploring some data augmentation techniques as well. And one other thing that we are trying to explore is that probably this super resolution based pipeline is not the only way to explore improved features for video classification on low resolution data sets. So we are exploring some other options like optical flow and stuff like that too. So this is the future work that we plan to do in the upcoming 2 weeks, and probably more than that. So we want to improvise our adversarial super resolution network. And first change that we're experimenting right now, which is the network which is currently training as well, we are replacing the student network with video swin, and that will combat the architectural differences between the student and teacher network. And we're also fine-tuning video swin, which was pre-trained on Kinetics 400 just on Tiny Virat, to do more fair baseline comparison with this new improved adversarial network. So this is how the new network will look like. It's not much different, but we're going to introduce some data augmentation techniques here. And we're going to also replace the student network with a video swin to see if we are able to improve our F score beyond 12%. One more thing that we are trying in parallel is trying something other than super resolution, which is optical flow based feature learning. So optical flow is nothing, but if you look at a tiny Virat video samples like this, we have written an algorithm which actually takes these videos and extract these optical flows for these video samples. And these varying colors are nothing, but they're trying to tell that what are the components or objects in this given video sample which are moving. And the direction of motion in this sample is like somehow pointed to this way. And the idea for going for this optical flow based solution in parallel is that probably projecting a low resolution video to high resolution is not the only way to do good on Tiny Virat video classification. But if we can just focus on the components which are moving in a video, that will help us avoid noisy low resolution pixels and deal with the low resolution problem of Tiny Virat. So this is the architecture which is currently training as well in parallel. And this is a modified version of original Vivid architecture for optical flow dataset. And it's nothing, we just have original temporal transformer here. And this whole is resembling to the spatial transformer in the original Vivid architecture, but we have kind of split it into two parts. So this right here, this one part of the spatial transformer is taking tubelets from the optical flow instead of original RGB videos. And here we have selected videos, clips from the original RGB sample. So we are currently on the initial epochs of this model's training as well, but if it gives us some improvement, we'll probably try and incorporate it into our super resolution pipeline as well. And these are references, and that's that.
So we are trying to apply transformers for instant segmentation on cellular data. So a few challenges with this data set that makes it hard for transformers. First off, for performing instant segmentation on cells. We have a very limited amount of data. So as you can see, we only have 50 images, and these all had to be hand annotated. And we're trying to see if transformers can help in this domain. So for the data, all the data is at the same scale. All the objects or cells are going to be found at similar sizes. We only have one image of each sample. And also to note, the number of objects here usually ranges around 700 per sample, which also makes it difficult for transformers to work. So the current baseline models that we've applied were the mask RCNN, which trained on 40 images. You can see a sample image, the predicted mask from that mask RCNN. So you can compare the ground truths. Our scores for our baseline model are found over here. So we're trying to see if transformers can outperform these scores. So for a baseline model, we were trying to take the MAS2 format, which was good for instant segmentation, and we're trying to modify it. So the first modification we made was applying the deformable encoder. The reason we went with this is because we can control what areas are being attended to keep it into a local region since cells are small. And by using deformable attention, we can also control the number of pixels we look at, which can keep parameters down. Second modification we'll go over in a minute is self-attention. Due to the high number of queries we have, the high number of cells per image, we need a high number of queries, which could result in bad runtime. So we made some modifications to self-attention. And lastly, due to the low resolution of our cells, we're changing what features we're extracting from the backbone. So typically they do stages 3 through 5. We're changing it to be stages 2 through 4, which gives us higher resolution features. The second change we're making is to the self-attention module. So we're trying to prevent self-attention from attending to every single query. We're trying to keep it into a local range. So we're trying to attend to the k nearest queries. So based on like an X and Y position, we only want to attend to the closest ones, since far away cells will not have an impact on this query. We don't need to adjust this query's position based on other queries that are far away. I'll pass it on to Tristan.
So we have a problem that we only have a low amount of training data. So to fix this data, we have simple augmentation, which is flipping, changing the scale and stuff like that. But a much more something that will give us better results is copy-paste. It's a published method that truly has an important improvement on results. So what we did here, we kind of take that copy-paste method and we apply it to our data. The thing is, our data is a little different from typical data. So there's something we're keeping, something we're not keeping, and something we're adding. For example, here they can change the scale. Because we have a single scale, we don't really want to do that, but we can create more background like they're doing. We can change the position. We can all do all that. And things we're gonna be able to add is flipping, rotating, and stuff like that, because you know, you can't flip a player, but for a cell that doesn't have really like a true up and down, there's no problem. So what it looks like is here, if we have one input image, I can take some of the instances, filter them, and create a new image, and then I'm gonna combine that from multiple images to create a new image like this. And I'm gonna do that over and over again, and that's gonna make us able to have more data that we actually have. And so that solves most of the problems. Now we're gonna talk about the progression that we made so far. So for the copy paste, at least, we're basically almost done. Then as Jacob mentioned, we're combining two models together and making modifications. So for the default mobile DTR, we installed it, we trained it on the Coco dataset, we modified the backbone like we wanted to, and now we're in progress of training it with our own dataset, which is those cells. And then when we have OMAS2 former, we're installed it, we trained it on Coco datasets, and we're training it right now with our cell dataset. We're adapting it because the type of data is different. So there's a lot of adaptation in the code, and that's what we're working on right now. And then we want to implement that method for supporting a large number of queries. And finally, we want to combine those two methods together, as Jacob explained. And then another thing we're doing, for example, is we're using the Swin transformer as another comparison model than sum of scores. And we're also running it with Coco dataset that we done, that was successful. And now we're trying to run it with our own data. So that's it for us. And here's a we're excited.
So we're doing DINO for video. And my group is Brandon, Joshua, Daguan, and my name is Alejandro. So our goal was to efficiently use features from a video, use self-supervised installation, and utilize or train on different downstream tasks. Our approach would be to use the DINO training regime and modify it to work with videos. There is a model that came out, or not a model, but like proposed method that came out that is called self-supervised video transformer, that basically implements DINO for video, and they did do the results on USIF 101. This was accepted this year, actually last month in March. And so so this happened, but the good things, we do have differences between that model, that proposed method, and our method. And so with the SVT, they keep the spatial cropping that was implemented in the original DINO. They vary frame rates of clips from the input video. They do a motion correspondent loss. They do a cross view correspondent loss, and then they do not implement on an object segmentation result. Our method, we redefine global and local views as temporal cropping. We have a DINO loss on spatial temporal features, and then we have an additional spatial attention loss. So this spatial attention loss, we compare overall features between the student and teacher model. Using video means we have to compare the spatial temporal features, and you want to maintain a good spatial feature for the video object detection. We compare similar frames of a video using features from the spatial encoder of Vivid. So how this is layered out is that we have the input with the global and the local crops. We feed that into the teacher and student model, which we can generate the spatial attention maps. Generate the same thing with the students. We generate the video features for each teacher and student model. With those features, we have the traditional DINO loss, and then on top of that, we can generate a spatial attention loss based off the two maps of the network. So the current status is that we've done experimentation with Vivid. We've used Vivid as a backbone on DINO. We fine-tuned it utilizing the linear classification head. We've got results from UCF 101. We are still experimenting with receiver on DINO. The implementation of receiver as a backbone on DINO is something that we were kind of exploring as using instead of Vivid. Currently working on the object detection fine-tuning. Vivid experiments with spatial loss, improving the perceiver's memory and training speed requirements. Perceiver is just a very memory hungry model. And experiments, we want to do experiments with performance on multiple domains, such as the action recognition, object segmentation, compare state of the art, performance, computational performance, and qualitative analysis of the intention maps and the task performance. I meant to say that. Down task experiments of action recognition, we add that linear classification head to the backbone model. We would fine tune this model using a subset of that data set. And then for object detection, we do we would use the Vivid as a backbone and existing video object detection model or methods. And then we fine tune this model architecture with a subset of those video object detection data set. And then for multi-model, we would utilize perceiver as a backbone for DINO, and we would utilize the audio and images as a multi-model input. And then we can add a classification head to that perceiver backbone for the action recognition. So for initial results on Vivid, which is what we've implemented so far, and this is what the spatial loss that we mentioned before on the ImageNet trained VIT weights. We trained on UCF 101 and our MFID, fine-tuned on 20% of the UCF 101 trained data. And so the accuracy was not great. It was 60%, but there's still some more fine-tuning that we could do to bump up that number. So the ablations, again, we're still experimenting with different backbones with that spatial loss, uniform frame sampling versus the tubelets. For perceiver, just the multimodal versus single modal. Well, that's the experiment. And so for our timeline, well, that's not really explaining. Yeah, pretty self-explanatory. And our references.
Okay, so we are Group F, comprised of myself, George, Fernando, and Sarah. And I'm going to be talking about Zesty VQA. So first, our project's main challenge focuses on zero-shot learning. So I want to remind everyone what zero-shot means in our context. So in our project, the task is to answer a question about a given image. And a zero-shot data set is one where at least one word in either the question or the answer has not been seen in the training set, right? So for example, our model might be given this image, and a possible question it might receive is, what color is the dog? Where our model has never seen the word dog in the question set. So it's going to have to, our model will have to infer what a dog is and hopefully produce the correct prediction. So now that we've defined what zero shot is, what is Zesty VQA? Zesty VQA, or zero shot transformer visual question answering, as its name implies, is a pure transformer model for answering questions about images. The image embeddings are fed into a shifted window transformer like SWIN, or exactly SWIN. The text embeddings are fed into a BERT. So as we can see here, right, that's kind of what this diagram shows. And the image and question features are fed into a transformer decoder here to obtain our image question features.
which are then sent to another transformer decoder along with our answer features that were extracted from this BERT here. And then everything from this point forward, we've seen before, right? So we just send it to an MLP, and then we predict our answer choices. So our plan is to compare our transformer against a baseline model that we used a CNN and LSTM model so that we can evaluate our model as a comparison. This model uses a CNN to extract the image features and then does a pointwise multiplication of the question features that are extracted from an LSTM. And then again, those image question features are multiplied with the answer features extracted from an LSTM. And it's kind of the same story here, right? So this gives us our image question answer features. And again, this is just our baseline model that we are trying to prove that transformers can outperform. So next, I'm going to go over some related work results. We recovered these results from another paper that attempted to tackle the same problem using LSTMs. A couple of key items to focus on are these, where LSTM Q plus I is similar to our CNN LSTM baseline, and also the author of this paper, this is their baseline model here. The reason this one is important is because our data sets compared to the authors of this paper are different, and it's difficult to find a common data set because zero shot implies that we're manipulating the data. So we had to kind of design our own CNN LSTM and compare it to this one so that we know that we have a reasonable baseline. And then this is kind of our target to beat so far. You can see that the standard split is a non-zero shot split. This is just a normal kind of VQA data set. The baseline CNN LSTM got a 52.1. Our competitor, so to speak, got a 59.5. And the zero shot splits are kind of divided up into a true zero shot split where the unseen information can come from the questions, answers, or the answer choices. This is the main one we're focusing on because we haven't split our data set into these specific categories yet. So our target for a zero shot split is to beat a 47.3. And so I'm quickly going to go over our preliminary results. One thing to note is that we included these here because we have multiple choice answers out of 4. So if we were to randomly choose, you'd see a 25% accuracy rate between normal or zero shot split. We can see that humans are able to achieve above like a 95% consistently. No real surprise there. This is our CNN LSTM. It achieved a 57.2 on training on Newton on our data set. Again, this is a slightly different data set than the paper mentioned before. And on the zero shot split, our CNN LSTM got a 52.7. Our initial run of our transformer got a 63.1 on normal split, so it's doing pretty well, and a 58.7 on zero shot. Again, doing pretty well. However, there's a couple of things that we want to look at to try to kind of maximize our performance. We want to fine tune hyperparameters such as the learning rate or number of heads and layers in our decoder. We would like to, given enough time, experiment with data augmentation, conduct some ablation studies with respect to the zero shot question split or answer split. We still need to do a little bit more data analysis on incorrect predictions in case there are maybe some underrepresented there's some underrepresented data. Obviously, we want to explore further into making our model more resilient to missing data. And here's our references for Swen and Bert and the previous papers I mentioned before.
So for our project, we're doing signature verification using a Siamese transformer architecture. And so we didn't include introduction stuff. We're just going over what the new things we did. So this is how we set up our model. So first we're taking each image. As you can see on the right, there's two types of images. There's a genuine signature and a forged signature. So we're gonna resize them. And then since most of the image is background white, we're gonna invert and normalize the images. And then we're gonna create pairs for genuine and forged. So one pair type is genuine, and the second pair type is genuine forged. So then our new data set will be 50% of the pairs genuine, and 50% genuine forged. And you'll see why we use pairs because of the architecture of the model and how we set up the loss function. So this is the architecture we're gonna be using. So I won't go over the transformers since that's just the basic stuff. So we take both images, put them through the transformer. Both transformers are identical, but right now we're not using shared attention. We don't know how exactly to apply that, but we're just using different unshared attention for now. And then we're going to do the classification head and take the Euclidean distance of the classification, and then use contrastive loss on that for training the transformer. So just to go over what the contrastive loss is. So you have three inputs. X1 and X2 are the images. So it'll be like one will be genuine, one will be forged, or both will be genuine. And then Y is, it determines, it identifies which type of pair it is. So a 1 means it's a genuine pair, and a 0 means it's a genuine forged pair. And then the dW is the distance. So we can use any distance equation. So, but right now we're using Euclidean distance. So the contrastive loss function, the purpose is to, when it sees a genuine pair, it wants to minimize the distance. And when it sees, which is on the, it's gonna be on the left, and on the right, when it sees a genuine forged pair, it wants to maximize the distance, which is on the right. So there are weights for both of these, but right now we're setting them at 1, alpha and beta. So it's equal right now. And alternative loss functions we've considered is triplet loss and quadruplet loss. But for each one of these, we would have to recreate the data set. So triplet loss, instead of pairs, it would be 3, and it would be 2 genuine, 1 forged. And then the second type would be 3 genuine, and quadruplet loss, it would be 2 of each. So 2 genuine, 2 forged. And yeah, but we're not doing that right now, but that's something we can consider. So just running right now, these are just preliminary results. It's very slow, and a lot of the parameters we haven't set up to optimize correctly yet. So this is the accuracy. CNN accuracy is what the CIGNET paper says they got when they run these data sets, 3 different data sets. And right now, these are the accuracies we're getting. We haven't done the CEDAR one, but we're getting 50% on both of these. And the next steps, So we're thinking maybe it's possible to use a CNN backbone or a different transformer architecture as the base. We're using Vision transformer, the base one, to get a better accuracy. And as I mentioned, the different distance and loss functions, and obviously our paper. And these are references.
Okay, good. I think this is a good presentation. It's pretty clear. And it's good. The problem is also clear. So now you guys have to try to push the results, right? Because right now it's a huge difference. So you have to figure out, how you can improve. Okay. So that's that. And so we will take a break.
Is my screen visible?
Yeah, but come closer to microphone. I think
Yeah, sure.
our audio is not that clear. Yeah.
Okay. So hello guys. Today I and Shuman from Group D will present the checkpoint 2 updates for our project called Seismic in Painting. This project is in association with FTAC. Through the quick recap, then our problem statement was to reconstruct waveforms coming from geophysical sensors. So basically, if the second graph is given as the input, we try to bring it back to the ground put, which is the first graph. We had a data set of 7,200 points, and we did upsampling and noise removal on those. A small recap of the architecture. Then this was the architecture that we were using in our last checkpoint. So here we had a swing unit based architecture, which had all the swing blocks, and we had implemented our own 1D shifting and 1D patch merging, and we were able to get some very decent results. Here were the results from checkpoint 1. These are the results from FTech model. We haven't run that model from our own. We have taken this image from the Jupyter notebook, which was shared to us. And these were the results that we had got previously. Coming to the updates of this checkpoint, we did a literature survey from other avenues, audio reconstruction, image in painting and stuff. We implemented discriminator, and we also developed a new model architecture, which we'll present today. So I have kept these references here. These are the papers we tried. We developed multiple architectures using that, but that was not useful. But we have kept because there's some great interesting work here. But I'm skipping this for interest in time. Then it was not working for us, so we went back to the implementation of the discriminator, as it was discussed in the future steps of our previous checkpoint. So as you can see, we got some very poor results on that after multiple different architectures. But the main issue that we suspect was because of the incompatibility between MSE loss and BCE loss. So, but we cannot drop any one of them because MSE we are using for reconstruction and BCE for classifying between real and fake. So we stepped aside and looked at the bigger picture and developed a completely new model. We are calling this model ZyNet. Xi is nothing but a Greek letter. As you can see that there are 3 pillars here, which are not connected, which is completely analogous to our architecture that we are proposing, very loosely connected 3 neural nets. So the main idea behind that architecture is to why not use both time and frequency to generate the patterns or generate the reconstruction. Okay, so take 2 of them and use a high dimensionality decoder, which will decode patterns in both time and frequency domain and reconstruct the image. So we could directly use the input mechanism that we were using earlier, but what about frequency? Now there were multiple options like go to a spectrogram and stuff, but we did not went to the spectrogram directly because we thought that combining the images data along with the numerical data would be ineffective. That was completely based on intuition. So we stick to the discrete time Fourier transform, and the problem there was like now all the real values were converted to the complex value. So then we did a trick to do the transformer encoder learning using complex value. So what we did was we took the real values from the complex values and put it all in the real plane, and the imaginary values into the imaginary plane. So basically a number now can be see through a depth axis r plus ij. And the remaining thing was nothing but doing a patch partition and passing it to the frequency encoder. This is the detailed architecture which we like discussed broadly earlier. So here was the time series encoder. Here is the frequency encoder, and here is that frequency converter along with the division. And this is the dimensionality, high dimensional decoder. Like here earlier it was 4C and now it's 8C dimensions. So this is the architecture that we developed, and we were able to get some pretty good results out of that. Time for results, but before that, let me tell you that we already analyzed all the results and have divided them into the buckets. So bucket-wise results are like type 1 is no change. So basically, here the third graph is the output from the previous checkpoint model, and the fourth one is the output from the present ZyNet model. And so basically where checkpoint 1 model was performing good, it still continues to do that in the new ZyNet architecture, but there are a lot of improvements, like it was able to perform corrections. In our previous model, if you can observe, like the pattern was detected, but the model was not able to reconstruct the image fully, but the ZyNet was able to do that. And in the right graph, we can see that the previous model output was completely wrong, literally inverse of the graph it provided. But ZyNet again was able to reconstruct that too. ZyNet also performed well when there were very less time patterns and frequency patterns like these. So previous model, it was just returning the gap itself with a little bit of manipulations. So here we assume that it's because there were patterns in this graph, but in the frequency domain. So ZyNet was able to generate those two also. And there were also some results where although the pattern was detected, but it was not able to regenerate the image fully. Like here, there were two peaks. It was able to detect two peaks, but it was not able to fully reconstruct the graph. Similarly, here the peaks are shifted a bit. So we think that this might get better if we do, let's say, iterative reconstruction, providing the output as it is back to the ZyNet, or maybe some other approaches like fine tuning and stuff. And we also got some downgraded results. So downgraded results were like the model where the previous model was performing better than the present ZyNet model, like in these examples, but the number of these downgraded results are around 1%, so it's very negligible. And so these were the results from the complete architecture that we have proposed. And coming to the novelties that we are trying to introduce through this architecture. So first of all, we are trying to do waveform reconstruction using transformers. It's not out there. We are attempting large gap filling. We are taking SWIN back to an NLP application. And we have done our own implementation of 1D window shifting and 1D patch merging. We have used multi-domain reconstruction. So basically we are using both time and frequency domain patterns. And we are doing our transformer is doing the attention with the complex numbers. So that's another plus. And these were all the introduction of the generalized architecture for waveform reconstruction. We are calling it ZyNet. And in conclusion, ZyNet was able to outperform both FTEX model and checkpoint 1 model that we previously showed. Only 1 to 2% results were downgraded as compared to checkpoint 1 models. So we are keeping this as final architecture. And the total number of waveforms that were previously reconstructed, that count has gone up by many folds. It's performing a lot better than previous one. But there was one special thing, like whenever the graph has less number of crust and trough, in that cases, our model is not able to perform better. So that we consider as the future work. And we think of doing like something like changing the window size dynamically. So that's the future work for us. And we'll also be doing the ablation studies on the present ZINET model. These were all the updates from our side. Thank you.
Okay.
Okay. I'll be presenting for our project single pass video repetitive activity counting with transformers. I'd like to quickly go over exactly what we're actually trying to accomplish here. Obviously predict the number of repetitions of an action within a video, improve upon state-of-the-art with transformers, but most importantly, what we're trying to do is accomplish this with a single pass, as opposed to other methods which use multiple passes, and I'll explain what that means. So just as an overview, the current state-of-the-art RepNet during evaluation, because it can only process 64 frames at a time, passes different cuts of the video over and over, and at the very end produces a periodicity. That means that they're going to take 64 frames, get the period length of each of those 64 frames, then do another 64 frames, and so on and so forth to get the repetition count of the whole video. Our goal is to eliminate that need and directly predict the period length. So in order to do our method, which is interpolate features so that we can just uniformly sample the whole video, we wanted to see if it was possible to just predict the sample rate of the video with just a 3D ConvNet. So predict either ×1, ×2, ×3, or ×4 sample rate or frame rate. And of course, we want to use this pre-training task to help with interpolation of features, because if we know how fast the video is sampled, we can know how many frames we need to fake, so to speak. And with ConvNets, it worked pretty well. As you can see on the left, it eventually got up to almost 55% accuracy. But we found that we couldn't seem to use a transformer to enrich these frames. And this led us down a path where we started to figure out that we couldn't replicate RepNet's state-of-the-art results to compare against. And for a refresh, their system basically looks like this. It's that self-similarity matrix where they just take all of their 64 frames, compare them against all the 64 frames, and then use a convolution to sort of figure out, based on this matrix here, what the periodicity is. So some of now obviously authors very often cherry pick the qualitative results they use, but for our implementation, some of the matrices clearly showed a kind of repetition going on, but then many of them did not. So we actually got together and met with the team at DeepMind, the RepNet authors, to figure out what exactly we weren't doing right. Why couldn't we replicate their results, and why wasn't our transformer method working? The first thing they mentioned is how they, which wasn't really explained well in the paper, is they actually randomly sample. They don't use different sample rates; they use different stride rates. So using a slice of 4 and then doing a sliding window to another slice of 4 frames. And also worth noting is that one of the reasons they said we probably weren't able to replicate their results is because Google doesn't let them release the best model they actually used, which we found very interesting. But so that probably explains why we couldn't replicate down to the the exact results they got. And then I'll skip over this because this was just hyperparameters. Okay. So after much trouble, we were able to actually, and with their help, get a 0.53 mean average error from RepNet. So that's with the predicted counts. So our goal is evaluate videos in a single pass with one sample, and we've come up with 2 approaches to do this. The number one is the one we showed last time, which is the feature interpolation at train time, and we've changed from actually using a GAN loss for that. And then the next one is S4 blocks, and I'll explain how we use those. So feature interpolation looks like this. We essentially add these tokens between each frame feature, and then we use a transformer to actually turn them into actual frame features. And then we have a discriminator create a loss from the real in between features. And we actually were able to match those RepNet results from before, which may not seem good, but keep in mind, we're using a single video pass where, they're using essentially 64 times 4 times 5 frames. We're just using a single uniform sampling. And oh, that was left in, sorry. Okay, so the second method we use actually comes down to this new method called a viz S4 former. And is introduced in CVPR 2022 and uses an NLP technique called an S4 layer. This is essentially linear self-attention. It massively reduces temporal overhead at the cost of a little bit of spatial understanding. And I wish I could explain it more in depth, but it's essentially modeling temporal relationship between features using some very clever matrix math. It's not very simple to explain, but it allows us to actually use almost 3 times the frames with the same amount of overhead during attention. And we actually, using this, we're able to get to 0.49 mean average error versus that 0.53 that we've recorded. So going forward, our interpolation result method matches their results without multiple passes. VisFormer approach improves by 5 points. We still don't match RepNet's reported results. So what we want to do is fine tune each model. We want to combine those two approaches and get results for each component.
All right, can you guys see my screen?
Yeah.
All right, great. So this is perceiverized decision transformer for reinforcement learning. A little bit of background again, we're using reinforcement learning to teach agents how to act in an environment to achieve some goal. A lot of the examples that we cover are simple games like Atari games, and we'll show some examples from a robotic simulation and also the custom environment that we created. Again, what we wanted to really address with our approach here is the limited context problem. So most reinforcement learning agents will simply use a single frame or a few number of parameters looking at one time step. And by looking at more than one time step, like previous frames, the agent can typically learn to do better. So the motivation behind using the decision transformer is moving from online to offline reinforcement learning, in which the agent would be actively playing the game versus looking at a supervised learning set, or I'm sorry, looking at a training set, which is now a supervised learning approach. And that definitely reduces the training time needed to train a model. It becomes a sequence problem where the transformer just needs to predict the next action that the agent needs to take, and we'll ask this network, given the current state of the environment, a history, and some desired reward, give us the action that yields the maximum result. So again, our approach was to take the decision transformer seen on the left here and adopt a more perceiverized input structure using the kind of flat input array and the cross attention mechanisms to do a much more efficient attention calculation. So we're still in the middle of implementing that part of it, and I'll show you. And the reason why is, again, to address those longer contexts where we can fit more previous frames and more information into those arrays. What we have done is finished creating our custom environments where we have basically a flexible navigation scenario where we have some platform. Our agent is in blue here. He's able to walk around this 2D or this 3D environment and navigate to some goal over here. Along the way, he's going to be able to look at a number of different objects or points of interest and decide whether to visit them or not. He may not have enough time as he steps across because he has a fixed step size. So he'll move +5 in X and +5 in Y every time step until he hits this goal. So he needs to make intelligent decisions as to which targets or which objects he views. So you can see he's visited a number of them in black here, and he has still missed 3. This was run using a greedy approach, and then I'll show you here what information is packed into that observation state that he can see once we train our model. So the agent knows his position in XYZ, where he's pointing that basically fake camera in azimuth and elevation. Some more information about the camera bounds in terms of angles relative to these pointing angles. And then he has some information about the targets, like the importance of that target, the position in X, Y, and Z, and then some state information like, have I visited it before? Is it within a 50-meter range, etc. So what we showed here is a sample metric is 7 out of 10 targets have been visited, so 3 have been missed. So you can see down here, we've hit 7 out of 10. And then we just finished the environment, so we were able to start training a proximal policy optimization agent, which is a baseline reinforcement learning agent on this. So we haven't evaluated it yet, but we have been able to start training with that. And then on to the actual decision transformer piece. We have been able to start training with the baseline decision transformer. The default training parameters, however, for the OpenAI Gym Hopper environment haven't yet yielded a competitive score. So in this environment, there are like 7 joint parameters that are modeled in the observation space and a couple controls that the agent is in charge of. And the goal of this is basically just to move this leg by hopping in the X direction as far as possible. So the paper reports like 800 plus units traveled in X right, versus training with those same parameters has only given us a score of 190 or 149. So we need to improve that before we can really even say if our next approach is going to work. Again, yeah, we're going to just increase default training iterations to hit better performance. And here are some of the metrics that we've run using different batch sizes. So batch size 64, 128, and 512. Training for a little bit, we've seen that it's pretty much always arriving at a similar evaluation score. And when we look at the training, that's just looking at the mean training performance. We see that the agent has hit 800, but in general, it's still performing relatively poorly. So we think that with more training time that this should be able to perform better. Next steps are just to finish up the GPT-2 to perceiver conversion, which is GPT-2 is the backbone to the decision transformer. After that, we'll train our decision transformer on that Hopper environment for longer. And then we'll test whether or not increasing the context helps by just appending previous state information to what the agent can see at any given time step. If we finish that, then we can demonstrate our custom environment, train our decision transformer on that, and compare that to the baseline PPO agent, which is much more simple and efficient. So it would be interesting to see how those two compare to each other. And that's it for me.
Yeah, so I think the problem with this project is it's too big. It's very big compared to for the class project. So it's very difficult to see that what exactly you'll be able to accomplish in 2 weeks. And of course, it's not really vision. You're using the reinforcement learning transformer. So, so you guys want to work on, be very, for the final, paper and presentation, be very precise that what exactly, you have done, because, there are lots of things you're talking about, and I kind of, see that you know what you're talking about. But in order for me to grade this and really, be convinced, so there has to be a smaller, short-term goal that, so your aim was to, what was the title of your project? Can you go back to that?
Yeah, I think that what would help would be
Yeah.
we focused on kind of the general environments where we could
Yeah.
control how big
Mhm.
that space is, but there are I think moving to the Atari environments, which
Mhm.
do use images, would probably be better then, right?
Mhm.
Because we can use images, and then
Mhm.
they don't use long context, like long histories of previous frames. So if we can update that GPT model to run
Mhm.
more efficiently with the perceiverized like attention mechanism, then it will,
Mhm.
I think it'd be more convincing that we can run like
Mhm.
longer contexts in images with images and show that is possible, and it's not a ridiculously huge model when you start to do self-attention, on multiple images.
Yeah, that probably will be a good idea, and come up with simple story. So GPT-2 you are using because you are using the text or something, like what why GPT-2?
Yeah, so that's the backbone that they use for the transformer in here. They just use that as the
So even though it
general
was
backbone.
this
Go ahead.
was GPT-2 is trained on the text, right? The language model or something. What's a GPT-2? Is a transformer, but I thought it's or it's a general transformer. GPT-3, I know it's a language. Yeah. So what's a GPT-2?
And it varies fairly similarly to a vision transformer from what I remember.
Yeah, I mean, what my thing is that GPT-2 is a language transformer. So how are you, using that? And maybe it seems other people have used it, right? That's what you're saying. This is left thing is the what.
As far as I understand from the paper, they just apply to a mask to those rewards, states, and actions in order to predict the next action to take. So it's similar to using language, to using it as a language model, but instead of using words, they're using these tokens instead.
And do they fine-tune GPT-2 for these tokens, or they just use that, convert tokens into language or something? How will this work? Like
in the paper, they just directly trained on their data sets and then evaluated on those data sets.
So they get a GPT-2 model and train it from scratch on these tokens.
Yeah.
Oh, okay. So they're not using the GPT-2, they are just using the architecture.
Yeah, it's not the weights, it's just the architecture.
Oh, okay, I get it. Okay, yeah, I think take these comments. So, I know you guys have done a good job in the paper presentation. This is a very big value, so make it, convincing that, you are doing something interesting for the class. Okay, very good. So we will, I think, end it here and see you guys next week. Okay, thank you. Bye.